Thank you. So thanks for inviting me back. It's always nice to be in Cambridge. And I figure since this is being put on by the ITC, I would have a bold, provocative statement that Bob kind of alluded to, that there are multiple progenitor systems for type 1a supernovae. And so I'll go from there and ignore a lot of the actual data that shows this, because there's going to be a panel later. And I'll start actually with something that is not a 1a, but is a white dwarf supernova, a thermonuclear supernova. This is 2012 Z. Here's the actual supernova. And it happened to have really deep pre-explosion images. It's a little bit hard to see with all the lights on. But we were able to detect the progenitor system here in pre-explosion images. It's the first time that we've been able to do this for a white dwarf supernova. And in this case, the best explanation that we have right now is that this is a single degenerate, one white dwarf, one more normal star. And I think that that's really informative, that for all of the 1As that we've detected, we have not seen a pre-explosion progenitor system. But for the couple dozen of 1AX supernovae, this is a weird kind of supernova, we have done that. So Rob will talk about this more in the afternoon. So, okay, so Bob mentioned a lot of great things about the fundamentals of type 1As, but one of which that he did not mention is that we really do think that they come from degenerate objects. In particular, we think carbon-oxygen white dwarfs. For decades, we've thought that theoretically, but recently we've had real observational constraints, where this is the light curve of 2011 FE at early times, that nice 1A in M101, where there are PTF detections showing it on the rise. And these blue lines are some sort of shock breakout or interaction model that constrains the radius of that star. This non-detection here is from PIRATE-CAM, this relatively small telescope that happened to be observing the field before PTF discovered the supernova. And that puts a constraint of 2/100ths of a solar radius, if you believe these models. Now, some people say, in fact, Tony's in the room, that you can potentially, depending on where you have this explosion, you can have a dark day, and so this isn't necessarily as constraining. But if you just take the observations at face value, you know that there has to be a degenerate companion. This is the phase space left over, a degenerate companion that a degenerate primary that exploded. And so that's real data, saying that these probably come from white dwarfs. We don't think they come from neutron stars. So that, I think that is fundamental. The other really important thing to note, and Bob touched on this as well, is that type 1A supernovae have a lot of diversity. Here are maximum light spectra of the more luminous objects, 91T-like, the fainter objects, 91BG-like, and normal kind of things, these branch normal things described by 94D. And you can see from the spectra that they look very different. And we know that most of this is because of a temperature difference in their photospheres. And that is related to the Phillips relation, this idea that slower declining light curves are, supernovae with slower declining light curves are more luminous, and those with faster declining light curves are less luminous. So we think that this is all dictated by nickel mass. The more luminous objects have more nickel. They're also hotter, whereas the less luminous objects create less nickel, and so they're cooler. Now, we know already that there has to be a connection between the progenitor systems and the explosions. We know this, and we've known this now for about 2 decades, because it's been shown very clearly that objects that are fainter are restricted to older environments. So the fainter objects tend to be in ellipticals and S0s, and you don't really see any faint objects in spiral galaxies. And there is just generally a trend that as you go to earlier galaxy types, the luminosity of the supernova goes down. So there has to be a connection between the explosions of type 1a supernovae in some sense and their large scale environments. So on top of this, Bob showed this picture of Tycho, this beautiful spherical explosion. And that's a 1A, but then this is Kepler. And we know that Kepler is also a 1A from X-ray spectroscopy, and it does not look like Tycho. It is not beautiful and spherical. And so it doesn't matter if this is necessarily dictated by the circumstellar environment or from the explosion itself, but there is definitely something different here in the distribution of matter in the remnant. And so the question is, are these different explosions? Are they different progenitors? But something is definitely different here. So now we can model the spectra and try to understand the composition of the ejecta. And so Paulo Mazzali has done this a while, and he's got this famous Zorro diagram where he plots the nickel mass as a function of this light curve shape parameter. And it shows the normal thing where the fainter objects have less nickel and the brighter objects have more. But then if you add up all the other elements, all the intermediate mass elements, silicon, calcium, things like that, the total mass for all these explosions seems to be relatively constant. So maybe there is some unique progenitor system, and you're just somehow dialing something related to the age of the progenitor or something like that, and that's changing the nickel mass. And so it's just something as simple as that. Maybe that's the case. Now, Bob showed some ideas for what you could do. We try to put these models for progenitor systems into roughly 2 camps, double degenerate, single degenerate. Here's my, I'm an observer, but this is a simulation of a double degenerate merger. The green is those gravitational waves that Bob was showing. So here we go. There we go. That's my simulation. Great, thank you. Stan's clapping, so I know that I did okay. So what you might expect from that situation is, because you have 2 white dwarfs, you wouldn't see something bright. Bob alluded to this. Here's the actual data for 11Fe. If you zoom in and in and in, the little circle there that you might not even be able to see is the positional uncertainty of 11Fe. And there's nothing nearby or anything there. And if you put this on a color magnitude diagram, the limit here, it's at almost absolute magnitude of 0 in the visual band. And it rules out not just massive star companions and massive star primaries, of course, but it rules out a lot of popular 1A progenitor systems like RSOF and things like that. They're just ruled out. They cannot be from this system. Now, we have similar measurements for 14J, the new 1A and M82, the closest 1A in 400 years. Where it's not quite as deep because there was a lot of dust reddening, but at cooler temperatures it actually goes deeper than 11Fe. Again, no detection. And Bob showed a similar image for supernova remnant 0509 in the LMC, and it's very beautiful. This has an interesting story where this picture was originally shown on the astronomy picture of the day, and then it resulted in this paper where they said, wow, I don't see anything. So when you look in close, so there's nothing really at the center. This is the center that they defined. There is a smudge here that turns out to be a background galaxy just photobombing this image. And there's no star to deep limits. Now, Danny's going to talk about this later, so I'll just mention that if you measure the delay time distribution, the time between star formation and explosion for supernovae, there's this very clear trend that at earlier times the rate was higher, and it's been decreasing for these longer delay times. And it's consistent with the double degenerate idea, which would have a t to the -1 distribution. And so I think Danny will go into this in detail, but there is that evidence and a lot of other evidence pointing to this double degenerate scenario. Now, an alternative, and this is just one of these single degenerate cases, where you could have some big star that has a wind, and maybe there's a little disk, maybe there's accretion that's hot. But again, let's simulate this, and when you have an explosion, among other things, one of the things that you might expect, you could have, maybe not in this case because I'm suggesting wind accretion, but you could have interaction with this companion. One thing that would definitely happen is you would ionize nearby material. The supernova at early times is very hot. You have a lot of UV flux, and that should ionize any circumstellar material that has a relatively low excitation energy. So we look at sodium. Of course, sodium, an alkali metal, has a very low excitation energy. And here's a very good case of 07LE. Josh Simon wrote this paper. It's not the first case or the only case of this variable sodium, where if you look at high resolution, this is relatively narrow sodium, D1 and D2, with time for this supernova. You can see this one line slowly getting stronger with time. And we interpret that as the sodium that was ionized recombining. And so then you see that absorption. And that's consistent with material very nearby. We don't see it in calcium H and K, which has a higher excitation energy and should not be as easily ionized. But we see it in sodium. And we've seen this for a handful of objects. And in fact, we've seen it for 12CG, the object that Bob talked about. So even if that wasn't companion interaction, we know that there's nearby material for that object. Okay, so it's great if you can have that time series of spectra, but it's very expensive to get a whole bunch of high resolution spectra for supernovae. So occasionally we just get a single spectrum for different objects, and we want to do something with those data. And so Asaf Sternberg wrote this paper where he classified objects based on their absorption relative to the deepest absorption component. So he would say if there's absorption to the blue of that deepest component, that it's a blue shifted line. If there's absorption to the red, it's red shifted. Maybe you have symmetric systems. Maybe you have just one single line. Maybe you have no absorption. And he posited that if you just had a supernova go off in some random galaxy, if there's a rotation curve of that galaxy, and so the supernova is on the back side of this galaxy, the light's going through, if it's rotating like this, you would see just the ISM moving away from you, and so you would see a red shifted line, and if it's moving towards you, you'd see a blue shifted line. And just statistically, if you had enough objects, they should average out, and you should see equal numbers of red shifted and blue shifted lines. And we see this in the Milky Way when we just look at random lines of sight with quasars and things like that. But when we look at type 1a supernovae, we don't see that. We see roughly twice as many blue shifted systems as we do red shifted systems. And the best explanation for this is that a large portion, roughly a quarter of type 1a supernovae, have outflowing gas. And so this, I think, is actually the best source of saying that there has to be some sort of circumstellar material, and it's probably, if you're just naive and you say what kind of a system this would be, you'd say single degenerate. Kin Shin, he has a great paper, an excellent paper that says how you can do this with a double degenerate system. I'm not going to go into detail about that though. What I am going to say though is, a while ago, in fact, while I was here as a postdoc, I examined these systems in a little bit different way, where if you classify them as blue shifted or red shifted based on their sodium, and then you look at their silicon velocity, which is, of course, a tracer of the kinetic energy per unit mass, what you find is that there are many more systems that are high velocity and blue shifted than that are blue shifted and low velocity. And you don't see any of these red shifted systems that are up here. I'll also point out that these circles are the variable sodium lines where we know that there's circumstellar material. And so there really is a connection. If you do a histogram of just objects that don't have high resolution spectra, those that have high resolution spectra in gray or in the blue shifted sample, you can see that the blue shifted sodium sample, they tend to have higher velocities. So there's not just this connection on bulk scales, on galactic scales of differences in the explosions, it's also in the progenitor system itself. Something related to the progenitor system affects what we're seeing. And immediately there are two scenarios that can explain this. The first one is that there are multiple progenitor channels where the progenitors with these outflows, these winds, produce more energetic explosions. You have that kinetic energy per unit mass that's just larger. Alternatively, if you want to have a single progenitor channel, the way to do this is you could have asymmetric explosions where higher velocity ejecta, those lines of sight, are aligned with winds. And that's feasible because you can imagine, your white dwarf has some spin or something, so there's some preferred direction, and then you could have a disk of material that's also aligned or misaligned with that preferred direction. But I would say that all of the evidence showing that there are at least some supernovae that are produced by double degenerate systems highly favor this first interpretation. Okay, so I pushed this a little bit further. Mark Phillips had this beautiful paper where he looked at the location of this gas. And what he found was for these blue shifted systems, the ones with the outflows, they were gas rich, that they had significantly more gas in their column for their extinction, so the amount of dust, than the red shifted systems in red, or even the galactic relationship, which is this black line. So they're just gas rich. Which makes sense if you have a lot of material near a relatively hot star or a super soft source or something like that, where the dust would be destroyed, but the gas would still be around. That makes sense. It's a different environment than the ISM. He also showed this beautiful result where he looked at the equivalent width, not the column, which is a little bit different, of course, where he again has the galactic relationship here, and that again, the blue-shifted systems tend to lie above the line. And so I looked at this a little bit further, and so here's that relationship, looking at all the high resolution observations, where the blue-shifted objects, which I'm saying are gas-rich, they are above the line. O9LE, we think, is actually something that has circumstellar material. The width of the sodium absorption is over 500 kilometers per second, which is hard to do from just ISM. And 12CG, like I said, it has variable sodium. So even though it's technically redshifted, we know that there's circumstellar material. So if you take that into account, really it's everything above this line has some indication of an outflow. Now the beautiful thing about this, I should say, is that the equivalent width here, you can measure that with a low resolution spectrum. You don't need a high resolution spectrum to do that. And the reddening here, you measure that from the light curve. So you don't need to spend an hour or two on an 8-meter class telescope to make these measurements anymore. You can spend 20 minutes on a 1.5-meter telescope, which is what essentially this sample is. This is the CFA sample making this measurement, and we can probabilistically determine if any object is gas-rich or gas-poor. And so then the beautiful thing about this, besides the fact that it is free, this is all literature data, is that these tend to be much more distant objects. And so we can finally look at the luminosities because we can go out into the Hubble flow and not have peculiar velocities be an issue. So just as a precursor, this is all in prep, if you do the same sample, if you cut instead of where we know blue shifted or red shifted, we just say gas rich, gas poor, you can again see this difference in the velocity for the sample, but now with significantly more objects, much higher statistics. Okay, so I'm going to switch gears now. So here is essentially all you need to know about supernova photospheres. This is a maximum light curve, maximum light spectrum that goes from the UV through the infrared, taken with both Hubble and Magellan. And if I'm going to stress the UV portion here because it tells us a lot of information. So here's that same spectrum on a log plot, and so for people who don't know this already. A supernova photosphere is very similar to a stellar photosphere where it's roughly a black body, but then you have, instead of narrow absorption lines from line transitions, they're broad and blue shifted absorption lines, but still very similar to a star. And then you have line blanketing in the blue, just like a star. And so Bob talked about how the infrared is great for cosmology because they're very, very standard there. I'm going to talk about how the UV is great for supernova physics because they're not standard there. So in particular, the progenitor metallicity really affects the UV, but does not affect the optical. The optical, most of the opacity there is electron scattering, whereas the UV, it's line scattering. And so when you have line absorption, if your metallicity is higher, that's going to affect your continuum. And so at higher metallicity, then your UV continuum just decreases, but it does not change the optical much. And alternatively, you can think about progenitor metallicity and how it affects the nucleosynthesis. As you increase the metallicity, of course, you have more neutrons. As you burn with more neutrons, a very obvious effect happens there. You get more stable iron group elements at the expense of nickel. So as you increase your metallicity, the amount of nickel mass goes, 56 nickel goes down. This is a robust prediction. This is just the nucleosynthesis. Now, the overall amount of iron group elements stays the same, though. It doesn't really matter if you have nickel 56 or nickel 58 or iron 54 or anything like that. They all have roughly the same atomic structure, and so the opacity is roughly the same. And so even though you can reduce the amount of nickel, and so changing the luminosity as you change metallicity, you wouldn't change the light curve shape. So for the light curve shape, you would expect a varying amount of metallicity should change the overall luminosity, where as you increase the metallicity, the luminosity goes down, but it does not change the light curve shape. So this should introduce intrinsic scatter in our Phillips relationship, just changing the metallicity of the progenitor. Now we get to tell the story of the data. In 2011, there were two very, very similar supernovae. 2011 FE, which we've talked about at length already, and then 2011 BY. And they are what we would call twin supernovae, at least in the optical. So here are two maximum light spectra, and there really are two curves. One's blue, one's black. They are more alike than any two type 1a supernovae I've ever seen, and I've seen a lot of type 1a supernova spectra. They really do look exactly the same. And the same goes for the light curves. The light curves, the color curves, these really look the same. They're slightly different, but there are squares and circles that represent the two objects here. So they look like they are twin objects. But if you just take the distances to these two galaxies at face value and you look at the absolute magnitude, the luminosity, they are very different. This is the absolute V-band magnitude for these two objects, where this difference is 6/10 of a magnitude, significantly larger than the scatter for type 1a supernovae. Now, one of the things that we thought might be a problem is that although 11FE has this beautiful Cepheid distance to it, the host galaxy for 11BY only had a Tully-Fisher measurement. We said, well, maybe that's the issue, and really this would go away. But we didn't just say, stop there and say, well, this has a big scatter and we don't know what's going on and it's probably an outlier, we'll throw it off the Hubble diagram, because we had UV spectra for both of these objects. So I just showed the optical before. This is going down into UV, and now you see even though the optical, they are identical, in the UV they differ. And so we can zoom in and see how much they differ. Right, they really start to change, around 2,500 angstroms. And so if you don't have UV spectroscopy, you would say these look exactly the same in every way. But with the UV, you can just say that they have different continuum, just like what was predicted for the metallicity. So we can look at the ratio of these two objects. We don't have to worry about the specifics of explosion models and things like that, because the two objects look identical. And so if you just compare object to object, you have this very nice clean measurement of the flux ratio as a function of wavelength. And we can compare that to these metallicity models, where again, if you do this flux ratio for the models, you get rid of the bulk characteristics of what happened in the explosion, and you're really just testing the metallicity. And so for specific models, the two objects indicate a metallicity difference of at least a factor of 30. In their progenitor stars. And that is consistent with this story, where you would have a different peak luminosity because of the different metallicity. And so we still said, this is an interesting case. We should do better than this 0.6. Let's get a Cepheid distance to that other galaxy. We did that. We measured it. I was hoping that this would just go away, but it didn't. It's not as large, 0.46 magnitudes, but that's still significantly bigger than the scatter. On top of that, now the error bars are so small that this is at least a 3.5 sigma result. It might even be higher depending on the correlated errors. I still haven't finished this. And the nickel masses, although they don't seem that different, they are something like a factor of 58% different for two objects that look identical in the optical. Okay, so we can continue this on. These two objects were beautiful because they were exactly the same. And so we could make this direct measurement. But for most objects, we don't have that ability. We have a bunch of UV spectra now. Here's the sample compared to some generic objects that we don't have UV spectra for in this plane of these two equivalent widths, which sort of tell you brighter objects and higher velocity objects. And we're starting to span this whole parameter space, although we're not done yet. In any case, if you say, I want to look at this object up here, how am I going to say if it's high or low metallicity? Because there's no twin object. So what we did is we took the entire sample of UV spectra here, and these colors correspond to the colors on the last plot if you were paying attention. And we tried to determine how this varies with different properties. So here's the same data, but I've color-coded it by their light curve shape. The lower luminosity faster decliners are in red, the higher luminosity slower decliners are in blue, the intermediate objects are in black. And you can see at least at some wavelengths there's a very clear trend that as you increase the peak luminosity around 3,000 angstroms, the flux changes significantly. There's more scatter in the UV, further in the UV, but there is a trend. And you can make a model a spectral model that just depends on a single parameter, the light curve shape. So when I've done this, now we don't need a twin. Really, we're comparing to the ensemble of the entire UV sample for any individual object. And so we can make direct comparisons now for all of these objects. We've done that. So here's just a subset. Again, here's 11FE and 11BY showing their differences in the UV compared to this model spectrum for their light curve shape. And then here are some fast decliners. They don't seem to have any differences across this entire wavelength range. They really look like they have the same metallicity. And then for slow decliners, here there is some diversity. And what we would say is that this one object, Assassin 14LP, appears to be the only other object that has some discrepant metallicity. It might be a little bit high metallicity. But we do need more data. If you're on the HST Tech, please look out for our program. And so hopefully soon we'll be able to continue to expand this out into the future. So since my time is up, I'll just put up my conclusions, and thank you all very much.
I'm looking at the image, the host galaxy for 2011 BY. It seems to be in a kind of edge-on spiral with dust lanes. Is that an issue in getting the normalization of the magnitudes right between the two supernovae?
So the magnitudes of the supernovae are very well constrained. They're incredibly high sampled light curves. Neither one has any indication of any host galaxy reddening at all. There's no sodium absorption. They have colors that are consistent with each other also. 11FE, we're fairly certain there's zero reddening. For two objects with exactly the same light curve shapes, exactly the same spectra, right? There was no reddening applied to that, and they line up perfectly. Their color curves line up perfectly. There's no indication of a difference in dust. If there were, you would have to have something where their intrinsic SEDs were counteracted exactly in the same way that the dust reddening law works. And so I just think that's impossible.
So you said you need a factor of 30 in metallicity. That's pretty tall order, isn't it?
So it's according to those models. But I don't know if it is, honestly. So if you formed one of those objects at redshift 4 in a low metallicity environment, and then you formed another one today, you might be able to get something that's very subsolar and then something that's slightly supersolar. So I would first say I don't know how much I trust those models, but then I would secondly say I don't know if 30 is crazy. It's high, but.
It's high, but.
So I just wanted to make a comment about the LMC remnant, the 1A remnant. So there's recent work by Rutgers grad student Luke Hovey and Jack Hughes doing an expansion analysis of the remnant, actually watching the remnant evolve. And the center, the Pagnotta and Schaefer center, may not be the full uncertainty. And so that center may get bigger in the future. So look out for that paper. And so there may be some stars that fall within the new error circle. So look out for that.
Okay, good.
I wanted to hearken back to your picture of Tycho and Kepler.
Okay, do you want me to go back to
that? That is the supernova remnants of the same. They look obviously different, but could that be a projection effect? Could Tycho look somewhat different if we looked at it from 90 degrees away from the way we are looking at it?
So I'm not a remnant expert, so I don't know if that's possible based on like kinematic data or things like that. But I do take light echo spectroscopy of these things, and so far we only have light echo spectra of Tycho. And as soon as I can, where's Armin? As soon as I can pin Armin down for a day or two, we can look at the supernova itself at maximum light, effectively, from all these different angles and see what the asymmetry is for Tycho. Now we have to find the light echoes for Kepler still, and then get the spectra of those and do the same experiment. And then we'll know at least if the supernovae are really very asymmetric, and I think that'll be a very interesting result. So if you're very interested, bug Armin.
Let me just comment. Just to add that they are different for many reasons. One, kinematically, okay, somewhat the same. I can't comment on that, but Kepler has a nitrogen-enriched material surrounding it, so one can kind of put it in this box of potentially interacting with some CSM material by a progenitor system. So in that fact alone, they are different.
Is this difference, can it be explained by just the ISM density? Difference between the two? And asymmetric on Kepler's side?
So again, I'm not an expert on this, but I believe that this has been modeled extensively, and as far as I understand it, it cannot be explained by ISM density. It has to be something more extreme.
Ryan, in the supernovae where you have evidence, you're probing the environment and winds, etc., are those thought to be coming from the non-degenerate companion or from the progenitor of the white dwarf or dwarfs? And then does that tell us something about time delays, because you still need to have that gas there?
Yeah, so this is an excellent question. So what I can say immediately is that for all of this objects where we've looked with high resolution spectra in ellipticals, none of them have sodium absorption. So that either points to the fact that there might be different progenitor systems, or what Ken would argue is that all right.
We've had a slide, so we can check.
That's a good question. So we have a model where in the double degenerate system, if you have a helium white dwarf companion that has a hydrogen, a little extra hydrogen, that's an ideal gas. That transfers first over, and then you can have a nova kind of explosion, and that'll expand out and sweep up ISM. And then you have a supernova however you want. As you sweep up, you're getting density enhancements. That density enhancement depends on the density of the ISM. And so if you're in an elliptical and you think that the ISM density is 0, then you don't sweep anything up and you don't see any lines. But if you're in a spiral where there's higher density, then you sweep more up and then you see these lines. So I think that that's a reasonable explanation. It's not the naive explanation that you would normally say that yes, these have to come from a single degenerate. But so I think we need to, if we found something in an elliptical with a strong sodium line, and especially if that were varying, I think that would be very indicative that it was single degenerate. Right, Ken? Is that a solid claim? Okay. All right.
That's good. Just one quick question, Ryan. You showed the twin supernovae, and you showed a single epoch. Now, supernovae evolve very differently.
Oh, yeah.
They can. And just how much of a twin are they throughout their stages? And I'm just wondering whether this came up in the analysis.
Yeah, so we have good spectral sequences for both of these objects. Melissa Graham wrote this excellent paper where she looked at the full data sets, and they look essentially identical all the way through, including in the nebular phase, which you might not expect if they had different nickel masses.
That's what I was curious about, going through the late phases.
One of the other data sets that she has is there's earlier UV spectra for both of them as well, and again they have the same discrepancy in the same sense, and in fact it's enhanced to a larger degree, which is what you would expect at earlier times.
Right.
So it's completely consistent with that model. I still don't understand the late, and all right, so if I can show quickly, here we go. So the late time decline, you'll notice if you even look at these blue curves, the decline rate is very different for these two objects. I don't understand that either. I've talked to people about this, maybe some magnetic fields that are increasing the positron capture or something like that, but this is very confusing to me.
At magnetic fields, we'll end it. Thank you very much, Ryan.
All right.
Let's thank the speaker.